Wanted to make some videos for you for the topics in homework 5 that we weren't able to get to. This video will cover increasing, decreasing, and constant functions. So, um, a function is increasing if it goes up from left to right. So that means from left to right, we are going up. That is an increasing function. And we always trace our functions from left to right. This is an important part of this definition. When you're identifying increasing and decreasing, you must be tracing your function from left to right. I'll kind of talk about that a little bit more in a second. But we're increasing if we go up from left to right. Similarly, a function is decreasing if it goes down from left to right. So as we trace the function from left to right, it goes down. And a function is constant if it stays flat from left to right. That means it does not go up, it does not come down. As you trace it from left to right, it is completely flat. Okay, and again, it's important with increasing and decreasing, especially that you trace your function from left to right. For instance, if I have a function that looks like this, um, sometimes students get confused about, let's say, this left half of the function. It's a little confusing because the arrow points down, you want to trace the function this way and say, oh, I'm decreasing because I'm going down and the arrow's pointing that way. So this is decreasing. But the arrow just means that this pattern continues forever. Um, Sorry, let me redraw that. The arrows just mean this function continues forever. If we are identifying increasing or decreasing, we must be tracing the function from left to right this way along our function, which means this left side of the graph here is increasing from left to right. I understand the arrow is pointing down, but that is not the way that we are tracing our functions. We trace our functions from left to right, so this left side is increasing. I think that's kind of the um, most often confused part of this from students. But again, the important part here is you trace your function from left to right. Always, always, always to evaluate increasing and decreasing. So let's try an example here. If we want to determine where the given function is increasing, decreasing, or constant, and we are going to use interval notation to do this. Okay, so let's start with, I'm going to change colors here because I think it's going to make this more clear. Let's start with where our function is increasing. Okay, so where here is our function increasing as it goes from left to right. So as we trace this thing from left to right, the places where we are increasing, we're going up from left to right, is this section right here and this section right here. Those are the two places where my function is increasing. And I think this got a little busy with the tracing, so I'm just going to simplify this a little bit. And just this section and this section are the increasing bits. So the way that we're going to refer to each of these, it says where the given function is increasing. That means we are going to refer to this by the x values. If we are talking about where something happens, we're usually going to be referring to the x value. Now, so what x values does this first increasing section of the graph cover? Well, if we trace this down, it starts at x equals -4, and it goes all the way up to here, which is x equals -1. So this increasing part covers from -4 to -1. So this function is increasing from -4 to -1. We're not going to include our endpoints here because at each of these endpoints, we're really neither increasing or decreasing or staying constant. We are in transition there. We're not going up or down. It's just we're switching. So we're not going to include the endpoints because we're not actively going up at our endpoints. Now, that's not the only section that increases. So we're also going to have to union this with another interval over here because I've got another piece of increasing right here. So this part where we're increasing starts at x equals 5 and covers up to x equals 7. So the next part where we're increasing is from x equals 5 to x equals 7. So these are the intervals where the function is increasing. Okay, so where is our function decreasing? Again, tracing our function from left to right. The place where we are going down is this section right here. So this is the place where we are decreasing. And again, we're going to refer to this by the x values that are covered. So this starts at x equals 1 and covers all the way to x equals 5. So we're decreasing from x equals 1 to 5. And again, not including the endpoints because we're not actively decreasing there. We're kind of in transition and making a turn. Okay, and then the last place we need to identify is where this function is constant. So again, constant means where we are flat from left to right. So this function is flat right here and up here. So let's start with this first bottom one down here. This flat area starts from x equals -5 and goes until x equals -4. So we're constant from -5 to -4. And then we have another section, so I'll union this with this section here, which goes from x equals -1 to x equals 1. So we're also constant from -1 to 1. All right, so that's how we identify where our function is increasing, decreasing, or constant. Trace your function from left to right, and then refer to each place where you're increasing or decreasing or constant by the x values that they cover. All right, and then the last one that I wanted to go over here is this last example. Where graphs can tell a story. So if we are given a story or an explanation and we want to choose the graph that um, represents that situation, I want you to be careful and pay attention to what your y values represent and how that relates to whether your function should be increasing, decreasing, or constant. Okay, so let's read this first scenario. Nicole is delivering a pizza to Mark's house. She drives at a constant speed toward the house until she stopped at a red light for several minutes. After that, she starts up again and drives at a faster speed than before until she reaches Mark's house. And we need to figure out which of these graphs best represents that. So again, I want you to pay attention to what our y values represent here. So we want to think about how the distance to Mark's house is changing through this scenario. So First, she drives at a constant speed toward the house. So if she's driving at a constant speed toward Mark's house, what's happening to the distance to Mark's house? Well, because she's driving toward Mark's house, the distance should be decreasing, right? Because if you're heading towards something, your distance from there goes down. So we should be decreasing at first as she drives toward at a constant speed toward the house. The only one of these functions that's decreasing at first is this one. So let's make sure the rest of this makes sense as well. So here's the part where she's driving at a constant speed and the distance to Mark's house is decreasing. And she's stopped at a red light for several minutes. So as she's stopped at a red light for several minutes, what's happening to the distance to Mark's house? Well, as time's passing, she's not getting any closer, which is why this is flat. The distance to Mark's house stays exactly the same. And then after that, she starts up again and drives at a faster speed than before. So as she drives faster toward Mark's house, the distance to Mark's house is decreasing, but it's even faster than before. So it's steeper than before. So I think this one makes sense. This is the correct answer to this question. All right, let's try another one of these. Number 2, Alonzo is working out by riding his bike. He starts by biking slowly at a constant rate. Then he gradually picks up speed until he reaches his peak speed. And then he maintains this peak speed for the rest of the workout. Okay, again, let's pay attention to what we are representing over here. So our y value here is the speed. So as we are going to go through this again, I want you to think about what is happening to his speed. Okay, so Alonzo starts by biking at a constant rate. So if he's biking at a constant rate, what's happening to his speed? If you're driving at a constant rate, your speed is not changing. So we want a graph that starts out with a flat speed. It's not changing, it's at a constant speed. So this one's constant, this one's constant, and this one's constant. So all of those are possibilities. This one is a no-go because it decreases at first. So that's not what we want. Okay, let's keep reading. He gradually picks up speed until he reaches his peak speed. So after we're constant, we should pick up speed. What does that mean as far as how your speed is changing? Well, if you pick up speed, that means you go faster, which means your speed should be increasing. So he gradually picks up speed. So we should be increasing after that. This is increasing. So is this one. Ooh, so is this one. So these are all still in the running. Okay, so then after he picks up speed until he reaches his peak speed, he maintains this peak speed for the rest of the workout. So if he maintains his peak speed, what's happening to your speed during that part? Well, if you maintain your speed, that means it's going to go flat again. And your speed is going to stay constant and it's not going to change if you maintain a speed. So this one never stops increasing. So that's not the one that we want. This one levels out. This looks good to me. Here's where he starts. He picks up speed until he reaches his max and then he stays there. That looks good to me. And then let's just check this last one. Here our speed is constant. Then we increase, but then this is still increasing. That's not a constant maintaining speed. So that one's not it. This one is, in fact, the correct answer to this problem. All right, y'all. That is the increasing, decreasing, and constant information for homework 5. I hope this helps, and I'll see you next time.